Let me just remind you that from this afternoon, we'll switch the Q&A with the lecture by Laura. So we'll have the lecture by Laura just after lunch, and then the Q&A after the coffee break.
Okay. Good morning. Yeah, I know it's difficult to do theoretical physics at 9 a.m. You might know what Pauli used to say, when he was asked to teach at 8 a.m. or 9 a.m. He said, usually, I don't stay up that late. Anyway, let's start. So, well, is there any question on what we discussed yesterday? So it was a little bit of everything, I know. It's always good, to go back to the basics. No, any urgent question that prevent you to sleep last night? No? Okay, good. Actually, yeah, I would like to go back a little bit, to the discussion that we had yesterday about Newton's universality of gravity. I think it's fine also to put things in perspective, in an historical perspective, right? Because what we learned yesterday is that basically the acceleration, the gravitational interaction times r squared, the distance to the center of gravitational potential, let's say, should be a constant, right? So that's what basically Newton understood, right? First of all, it was not an easy step because, we take for granted that acceleration is a physical quantity, but Newton himself invented this notion of acceleration, right? So that's something that took place in 1987, I think, right? This Newton's second law of mechanics. Newton's second law, right? And then I wanted to tell you that actually this is also another way, let's say, to formulate this Kepler third law of whatever, celestial mechanics, right? So Kepler third law, I think this is 1619, right? So you notice by just measuring the orbit of various planets that the orbital time squared times r cubed was a constant, right? So that's just an empirical thing. Okay, he has simplified the fact that, in principle, the orbits are just elliptic. So now it takes just the circular limit. So it's just a circle. And that's what you get. And actually now using Newton's universal law, you can also compute that this quantity is indeed a constant, and it's just the Newton constant times the mass, so the mass of the mass of the sun, or whatever, the mass of the earth, if you want, whatever, the center of the potential, times 4 pi, right? Divided by 4 pi squared. And yeah, if you remember, yesterday I asked you to think a little bit about the expression of the acceleration. So the acceleration, it's a distance divided by a time squared. So the distance, usually it will be the orbit length. And then the time, the typical time that you have at your disposal is the orbit period, right? So let's say for a circular orbit, so it will be 2 pi r divided by t squared, right? But then I told you that actually this is not a correct expression. There is this magical factor of 2 pi that you need to add, right? It's just Pythagoras. This factor of 2 pi is just the Pythagoras theorem that is telling you. Just that you have a cycle here, so you have an acceleration, to the center of the motion, and then you have the speed here, which is perpendicular to the motion, and then clearly here you have a rectangular triangle, so you need to use Pythagoras, and Pythagoras is really giving you this factor, this extra factor of 2 pi, so this means that it's 4 pi squared, and that's exactly this 4 pi squared that you will find here, right? So I think, it's really nice to see all these famous people, right? Pythagoras here, there is Kepler, Newton, everything is really connected with each other, right? But just imagine a little bit what was the feeling, right, of Newton when he has understood that indeed these things is just a constant, right? It's just a constant. He applied to the moon, or it applied to the apple falling on Earth, right? You just put the numbers, and you find that indeed this is a universal theory, right? Universal behavior. I think it must have been a very thrilling moment in his life, right? Of course, physics is an experimental science, right? So you need to put the numbers, and that's something that I don't really know. I mean, it will be interesting to go back in the literature and to understand to which extent, I mean, to which accuracy actually Newton now knew, for instance, the radius of the Earth, the mass of the Earth, the distance between the Earth and the Moon. So to which extent, I mean, this constant was really a constant within the error bars, within the experimental error bars that were known at that time. So I think it's a very interesting things to do for you to look back in the literature. Okay, so now we need to move forward in time and to come back to the 20th century and to understand particle physics, right? So at the end of the day, standard model is actually a good abbreviation of special relativity plus quantum mechanics, right? So that's really the meaning of standard model. It's just really the combination of special relativity and quantum mechanics. So yesterday I've already talked a little bit about the usual characters, usual elementary particle that we are dealing with. So of course, the notion of elementary particle evolved with time. I mean, the elementary particle at the beginning of the 20th century are not exactly the same as the one that we know today. So the standard model is actually a time-dependent statement. I'm talking about the standard model as we know it today, and hopefully I really hoping that, I don't know, in 10 years from now, the standard model will be different, right? So we are talking about BSM, but BSM is something that doesn't exist because as soon as something else is discovered, it will become part of the standard model. Anyway, so the usual character that we have already introduced are the electron, and then there is the up quark, the down quark, right? So the proton, the neutron are made of quarks. I mean, I'm sure you have already know about that. There is also this neutrino electron that we introduced yesterday, to make sure that in beta decay, energy and momentum are conserved. So these are, the particle that the usual, the stuff that the usual matter is made of, right? So the stuff of usual matter. Usual matter. And then what was discovered also, is that there are other elementary particles that are produced in stars or that are produced in colliders, right? So the colliders are also stars themselves, in a sense. So the amazing thing is that, there are particles that have exactly the same quantum numbers, the same characteristic that we are going to discuss in the next lecture. So they are, the same property under the fundamental forces. And then the difference is just that they are heavier siblings of those usual matter, right? So there is, for instance, here the muon, the neutrino associated to the muon, the charm and the strange quark, and then there is the tau, the neutrino tau, the top and the bottom, right? So these are heavier particles that, again, they don't usually exist in nature. You need to produce them. You can produce them, and they live in a very short amount of time. They usually decay into the usual matter. Right? So these are what is usually called the matter particle, and then there are all particles associated to the force. So there is a photon, the W and the Z, the gluon. You could also add the graviton to some extent, but the graviton is not really part of the standard model because gravity is not included per se in the standard model. It's just an external force. You can couple gravity to the standard model, but it's just external. And then, as you know, there is also the Higgs boson, right, that has been discovered. So that was just to to put on the blackboard all the particles that we are going to discuss and that we are going to encounter into this discussion. Okay, so I think that's more or less all what I wanted to tell you. So where we left yesterday was this amazing discovery that there is, again, a universal force that controls the decay of the muon and the decay of the neutron. And that was noticed by, again, a universal relation, something, that remain constant, even though you are discussing apparently two different phenomena. Right? So this miraculous was simply to note that the width of the muon divided by the mass of the muon to the 5th power was equal to the width of the neutron divided by the mass difference between the neutron and the proton to the 5th. Right? And that is supposed to be equal to this constant G Fermi that we introduced, and then there is some factor, numerical factor due to phase space numbers. Okay, so again, that's an empirical relation. People have measured all these quantities, and they found that this equality. And the way to understand that is really by introducing a Lagrangian, an interaction that is responsible for those decay. And this interaction, as we wrote it yesterday, was just G Fermi times, let's say, some interaction that involved in those decays. So it was neutron, proton, electron, neutrino, for instance, right? Okay, here I need to put some bars, let's say. So there are various things. First of all, here, this kind of relation is totally fine for the muon because the muon, the electron, and the neutrino are elementary particles. This equality here is not totally exact because the proton and the neutron are not elementary particles, as we know today. The proton and the neutron are actually made of quark, right? So there is some form factor that actually describe, how the quark are bound together to form actually the proton and the neutron. So here there is a little bit of, non-perturbative physics that enter that, you cannot really compute in perturbation theory. You need to rely on lattice, on things like that. And so there is some fudge factor, which is not exactly this factor. But it turns out that actually for the neutron decay, this is a pretty good approximation. This form factor number is close to 1, actually. So it's not an issue, fortunately, because this allows us to really understand Fermi interaction. Okay, so now we'd like to dig a little bit more into the structure of this interaction. I didn't pay much attention. So it's true that here, as we described, to understand that, we really understood that all these particles involved in those interactions are spin 1 half particles. So they are described by Dirac spinors, right? So spin 1 half Dirac spinor. And again, looking at how the spinors transform the Lorentz transformation, you can try to build something which is invariant in the Lorentz transformation. So it's certainly true that out of 4 spinors, there is various ways to actually contract and make something which is invariant in the Lorentz transformation. So here is one, but there is actually several other possibilities that you can write. Right? For instance, you could insert some gamma matrices like that, with E, gamma mu, nu E. So that's another possibility, out of 4 spinors to form a scalars. You could also use something which is n bar gamma mu 1 minus gamma 5, let's say, P, right? Electron gamma mu 1 minus gamma 5 nu E, right? So these are objects, that again are totally invariant under Lorentz transformation. So by analogy, let's say with electromagnetism, with the exchange of a photon, people saw that actually that this Fermi theory were actually corresponding to a current-current interaction. So here you have something which is a current. You have another current. So this is the electron current. Let's say the proton and neutron current. And then you contract these two currents. So here you can say it's J mu. J mu. Right? So this universality really of the weak interaction, the fact that you have the same G Fermi that control both the decay of the neutron and the muon, was pointing or was indicating that the current for the weak interaction was universal. So it was something like neutron gamma mu P plus neutron, muon gamma mu. So there is a lot of mu, but these are two different mu's, right? So this is a space-time index. This is a muon, right? Don't confuse things. Plus electron gamma mu nu E. Right? So again, this universality of the weak interaction is basically telling you that you should find the same coefficient in front of all these terms in the current. Well, I mean, to some extent, that you have a +1 here is just a normalization issue. I mean, if you had a different factor, you could always factor it out in G Fermi. But really the amazing thing is that you have the same coefficient in front of the muon and the coefficient in front of the electron. Right? And now, indeed, if you take the squared, in the squared, you will have this mixed term. Well, this one with this one will be responsible for neutron decay. Then the mixed term here and here will be responsible for the muon decay. Right? So again, you have a universal current, and this universal current exactly reproduces what we know. And there is a single unknown at the end of the day, which is G Fermi. Right? And now you can measure G Fermi directly by either the muon lifetime or the neutron lifetime, and you will find that G Fermi is something like 10 to minus 5 GV minus 2, right? So as we saw yesterday, G Fermi has a dimension of the inverse of a mass, so it's the inverse of an energy. So that's why it's GV2 minus 2. Okay? Good. So again, here it's really this universality, right? Universality is really dictating this relative coefficient in the different terms that appears in the weak current, right? So this is called the weak current. Okay. So now that we have this nice theory, we also have a prediction, right? Because I still need to take the squared of this current, and the Lagrangian is the squared of this current. So far, I've really focused on the mixed term, or the cross term, this times this, or this times that. But there is also the squared of the individual terms, right? So now what is happening, right? So this J mu, so G Fermi, J mu, will contain a piece which is electron gamma mu nu E. And there is a complex conjugate, so it's nu E gamma mu E, right? So it means that you have an interaction among two electrons and two neutrinos. So you could have a scattering of, scattering of electron over neutrino. Oh, what was the experiment that was done? Yeah. Nu E electron scattering over nu E electron. Right? So you have an incoming beam of electron and neutrino going out and giving an electron and a neutrino. So now let's try to compute the cross-section for this process. Right? So now it's not a decay, it's a cross-section. So you have two beams of particles, and you want to find the probability of interacting for those particles. Right? So cross-section, sigma, has just the dimension of an area. I mean, the cross-section is just the size of the object, right? The classical size of the object, if you want. So sigma is just mass dimension to -2. Right? So again, by dimensional analysis, right, this should also be proportional to G Fermi squared, right? Because the amplitude involves 1 power of G Fermi, right? Is this interaction. So there is G Fermi here. So that's the amplitude, and then you take the squared to get a cross-section or to get a decay width. So it's G Fermi, and G Fermi is m to -4. So to make it consistent, it means that this cross-section should go like a squared of an energy, a squared of a mass, right? So at low energy, when the electron and the neutrino have energy which is small compared to their mass, here you could think of putting the mass of the electron or the mass of the neutrino. But what I'm interested in is what is happening when I crank up the energy of the electrons, crank up the energy of the beams, right? So then you can assume that the energy is much larger than the mass, and then the relevant energy that you have at your disposal is really the energy of the beam, right? So it means that the cross-section here should go like G Fermi squared times energy squared. Right? That's the only thing that is consistent with dimension again. Right? So m to -2. Right? And now you start seeing a problem here, right? Because you have a cross-section, right, that grows with the energy. The cross-section is, more or less is a probability of interacting. Right? Probability of an interaction. So certainly a probability, as you know from math, probability has to be smaller than 1, right? It means that you cannot have a cross-section that grows with the energy indefinitely. It means that the theory here has a cutoff. The theory, so this Lagrangian that describes those interactions, is valid only up to a given energy, at which the probability will become of order 1. At energy above that, your theory doesn't make sense, so you probably need to change your theory to get something which remains consistent with math, right? And here, actually, we can do a little bit more, right? We can actually estimate the energy at which the theory breaks down, right? It breaks down at energy, basically, where the quantum correction will become of the same order as a classical contribution to this scattering process, right? So here, so you have the classical processes, and neutrino, electron, neutrino, electron. So that's the classical thing. And then you have this virtual particle due to quantum mechanics, a combination of quantum mechanics and special relativity. Right? Certainly you have a diagram like that. Neutrino, electron, neutrino, electron, neutrino, electron. Right? So that will be a one-loop correction to this scattering process. Right? So here is proportional to G Fermi. Well, okay. We'll compute the cross-section, so it will be proportional to G Fermi squared E squared. What about this other diagram? So the diagram involves 2 power of G Fermi, and then you need to take a squared to get the squared of the amplitude. So it will be G Fermi to the 4th. And then, again, by consistency, so G Fermi to the 4 is m to -4. So here, you think it should be a 4, 6, no. So I need 2, 8, 6, right? So e to the 6th. And then, okay, there is one loop factor, so it's probably divided by 16 pi squared, right? So you see that this quantum correction will become of the same order as the classical contribution when the energy, this term is of the order of this, right? So that's the cutoff, that's the maximum energy at which this theory makes sense. Cutoff, whatever. And this is what, so the maximum energy is, so 16 pi squared G Fermi, G Fermi 16 pi squared is of the order of G Fermi squared e to the fourth, right? It means that E is square root of 16 pi squared divided by G Fermi. 16 is 4 pi, right? So it means that really I have a maximum energy at which this Lagrangian, this phenomenological interaction can be used to compute some processes. At energy above that, the theory breaks down, it doesn't make sense. Right? And so if you put the numbers, this should be of the order of, yes, few hundred GeV, right? Few, whatever, 3, 2, I don't know exactly the numbers, but let's say 200 GeV. Right. So in a sense, I mean, Fermi already knew, when he wrote his 4 Fermi interaction, that at some point he will discover something new. Right? There will be some new phenomena that occur at energy below, let's say 200 GeV, maybe 1 TeV. I mean, this is not very precise. I mean, at which stage you are really losing control on perturbation theory? Is it when the two contributions are equal, or whether this is 1/10 of the other? So there is always, an uncertainty, a number of order 1 that you put. Depends how accurate you want your theory to really describe what you are computing. Right? But anyway, I mean, at energy of this order, you should find something else in addition, let's say, to nuclear physics, right? Something else in addition to the decay of the muon or the decay of the neutron. Right? So it's not an accident, of course, that later on, I mean, LEP or LHC at the end of the day discover something else. I mean, it was first the discovery of the W and the Z, right? The gauge boson, which are actually responsible for generating this 4 Fermi interaction. So the 4 Fermi interaction is not a fundamental interaction. It's something which is valid only at low energy. Right? And what is really generating this 4 Fermi interaction is simply the exchange of a gauge boson that has been called the W and the Z. Right? So, I mean, the W and the Z were discovered in 81 or 82 at an experiment at CERN, which is called UA1 and UA2. I think Laura didn't include this experiment in a nice table yesterday, but that was really, I mean, a fundamental experiment that really established, in a sense, the standard model. And that's why, for instance, Carlo Rubbia and Van der Meer, that built this experiment, got the Nobel Prize, right, in 84, I think. And then, LEPT really measure all the interaction of the W and the Z, and later on, the LHC discovers the Higgs boson. Right? So we are going to see where the Higgs boson actually fit into this story. Right? It's a very interesting story. Okay. Any question? Yeah. Is it clear? Right. So I should warn you, first of all, that this is not yet the end of the story. I've written this weak current, assuming that this vector, right, so it's gamma mu. Actually, we are going to discover that it's a little bit more complicated. Actually, it's a mixture of this vector and axial current. But for that, I need to discuss something else, which is a pion decay. Right, so it's just another experimental fact. Okay. Good. So, yeah. So the trouble is really this interaction, this 4 Fermi interaction, and the trouble at the end of the day is that the coefficient in front of this interaction has a dimension, right? Has a mass dimension, or the inverse of the mass squared, right? So this is what we call usually a non-renormalizable interaction. So it's an interaction that cannot be extrapolated up to very high energy. And that's, of course, something that doesn't occur in electromagnetism. Electromagnetism has, let's say, a coupling constant, which is the electric charge. The electric charge is 1.6 10 to minus 19 Coulomb. But actually, Coulomb is just a dimensionless unit when you put h bar is equal to c is equal to 1. Right? So if you have done your homework, in natural unit of high energy physics, the electric charge is equal to 1/3. So it's much simpler than 1.6 10 to minus 19, right? That's why, physicists have been smart with using the right units to have numbers that are of order 1, right? By the way, I've done the exercise of CFIR yesterday, so 1 parsec is 10 to minus 23 electron volt, right? And if you also want to convert, because he computed, nicely this energy density of the vacuum, milli electron volt, it turns out that it's more or less the same order of magnitude as the energy, let's say, of the radiation. It's 10 to minus 4. I think you say omega radiation is 10 to minus 4, right? But 3 Kelvin, right? That 3 Kelvin is the temperature of the radiation. So 3 Kelvin, if you use the Boltzmann constant, correspond to 10 to minus 4 electron volt, right? So everything is consistent, right? 10 to minus 4 electron volt is indeed consistent with the vacuum energy that CFIR derived from observing the supernovae, right? So it's always, very helpful to be able, to have a system of units where everything connects with each other, right? So that's why this electron volt is the right unit to do interesting physics. Okay, so what else? Yes. So now we want really to understand this 4 Fermi interaction. So what is the structure where this 4 Fermi interaction is coming from, right? Right? So instead of having, let's say, a contact interaction, what we want to see is that actually there is a new particle which is exchanged, and that is producing this interaction. So this is nothing else as at low energy, so at E smaller than probably this cutoff energy, right? So G Fermi minus 1/2, right? We want to see that this is actually nothing else than the exchange of a gauge boson. So you have a particle which is exchanged exactly like in electromagnetism when you're exchanging the photons. So the only difference now compared to electromagnetism is that here, this particle which is exchanged in this process actually has a mass. So the photon is massless, as you know. Electromagnetism is a very long-range force. So you can never go into this limit where you have energy which is smaller than the mass of the photon, because the photon is massless. But here, we'll have a new gauge boson, which is massive, and actually its mass will be related to the value of G Fermi. So at energy which is much smaller than the mass of the particle, we don't have enough energy to excite this particle. So this gauge boson cannot travel, in a sense, right? You have no energy to excite this particle. So actually, it doesn't travel. So it means that this exchange is just shrinking to a point, right? So that's why here, at low energy, everything appears like a contact interaction. But if you have enough energy, if you have energy to excite this gauge boson, you can see that actually, in reality, there is really a gauge boson which is propagating. Okay, so let's call here. So here we have a neutrino, an electron, right? Neutrino, electron, neutrino, electron, neutrino, electron, right? So here, I want to have a new gauge boson that we'll call W. So let's see and try to understand what are the characteristics of this gauge boson, right? And for that, let's look at the electric charge of these various particles. So the neutrino has actually an electric charge which is exactly equal to 0. But that's why it was difficult to see it, right? Because it doesn't interact with light. Doesn't interact with the photon. So the electric charge of the neutrino is 0. The electric charge of the electron is -1, right? So if you want to conserve electric charge, it means that here, these W gauge boson also need to carry an electric charge, right? So you want to conserve here, on this vertex, right? Here and here, you want to conserve electric charge. So this is telling you that W has an electric charge which is -1. So that's something which is totally different than photon, right? The photon has 0 electric charge. The photon doesn't interact with itself. Right? Electromagnetism, right? This basic law of electromagnetism is telling you that the photon interacts with the particle proportionally to the electric charge of those particles. So since the photon has 0 electric charge, it doesn't interact with itself, at least classically. Quantum mechanically, you can generate what is called this Euler Heisenberg-Lagrangian, where photon or light by light scattering, right? The light can scatter on itself, but that's really a purely quantum mechanical phenomena. By the way, the photon people are always excited to see this light by light scattering, but that's something that was observed already at the LHC in heavy ion collision, right? That's the first experiment that really saw this light by light scattering processes. Okay, yes. So let's try to understand now the structure of those gauge interactions, which are mediated by this gauge boson. So again, here I'm using this principle that the gauge field is associated to symmetry. Symmetry is associated to a force, right? Something that we discussed a little bit yesterday during the Q&A session. It's not totally obvious, but here that's really the formalism that I want to use. I want to find the symmetry which is associated to this gauge boson, right? And as I say, has to be something different than QED, than electromagnetism, because this gauge boson will interact with a photon, because this W gauge boson an electric charge. So everything that has an electric charge will interact with a photon. More precisely, we'll have something like that, right? W minus, actually the antiparticle of the W minus, which is called W plus, right? I mean, we have already understood yesterday that every time you have special relativity and quantum mechanics, you have antiparticle. So if you have a W minus, you should have a W plus that exists also in nature. This will be the antiparticle of the W minus. Right? And this will interact with a photon. Right? That you have no choice, right? It's, again, basic conservation. No, conservation of the electric charge tells you that you are predicting this kind of interactions. And here, that's something really that doesn't occur in electromagnetism, right? So remember yesterday, when we construct the Lagrangian for the photon, it was minus 1/4 F mu nu, F mu nu, and F mu nu was simply d mu a nu minus d nu a mu. So this Lagrangian is only quadratic in the photons. Right? There is one photon here, one photon here. The Lagrangian stop here. There is no interaction among the photons. So that's one prediction, let's say, of QED. Right? At the classical level, the photons don't interact with themselves. So here, I have something new. Right? I have an interaction among three gauge bosons. And that actually is a signature of a non-abelian interactions. Right? So yesterday, the way we constructed QED, right? QED was simply by requiring that the wave function, let's say, of the electron, psi e, could be changed by I theta of x, psi e, right? So it's a local interaction, but that's an abelian interaction. I can perform two transformations of this type and commute them. Doesn't matter in which order I do those two transformations. So this is an abelian gauge theory. Abelian gauge symmetries. And for those abelian gauge symmetries, I don't have gauge boson self-interaction. So here it's an indication, the fact that this vertex exists is an indication that actually I have a symmetry that is non-abelian. I need to add something a little bit more complicated to really be able to describe these W interactions. So very quickly, I will tell you about non-abelian gauge interaction. Just a simple generalization of QED. You just need to transform various particles into each other. So let's say I have a field phi, which is just a collection of various particles, right? So if you want, it's a vector. It could be, I don't know, the neutrino, the electron. It could be a quark up and the quark down. And I'm looking at transformation that will mix those various components of the vector. So U will now be a matrix, right? So if you want, you can put some indices here, is I, J, phi, J, right? So it's really a matrix. And it's a matrix that will depend on space-time. So if you want, I mean, QED, electromagnetism, is just a matrix which is proportional to identity. Or more generally, a diagonal matrix, right? I mean, different particles could have different electric charge, but really the transformation is diagonal. So here, I'm allowing myself to have a non-diagonal transformation of the field. Okay? And an important quantity, that we introduced yesterday to make the Lagrangian invariant under this local transformation was to promote the usual space-time derivative to covariant derivative, right? So for QED, we had d mu phi that was actually becoming d mu, that was replaced by d mu phi, that is d mu phi plus I, whatever, the electric charge now, a mu phi. Right? So now I want to do something similar for non-abelian interaction. So that typically will be, I don't know, non-abelian, right? Okay. That will apply to QCD, that will apply to the weak interaction also. D mu phi will be d mu phi plus I, J, that will be the gauge coupling of this new gauge interaction, a mu phi. The only difference now is that a mu is a matrix, right? So here it was just a function, it was diagonal. Now it's really a matrix with non-diagonal element, right? And I'm looking at the transformation property of a mu in such a way that the covariant derivative will have a transformation property very similar to the one of the fields themselves. So I want d mu phi, to transform as u d mu phi. And again, that's, so you are choosing really the transformation property of a mu in such a way that this covariant derivative transforms homogeneously, right? Doesn't involve any derivative of acting on mu, on this gauge transformation u. So it's a very simple exercise to see that this is true if and only if a mu itself transforms in the following way. So a mu goes into a prime mu, which is equal to what? U, a mu u minus 1 plus I over j d mu u minus 1. Right? So you recover clearly the case of QED, if U is a diagonal matrix. So in this case, everything is diagonal, so you can move U, you can commute A with U, and then you have U times U minus 1, this is A mu. And then here is simply the derivative of the phase. Right? So d mu of theta. So that's really the non-abelian generalization of gauge transformation. So why do we insist that the gauge field, or that the covariant derivative transform in this way? Well, it's just to be able to write very easily a Lagrangian which is invariant under those local transformations. So again, d mu phi dagger d mu phi will be directly invariant if the covariant derivative transforms in this way, right? Because this goes into d mu phi dagger, u dagger, u d mu phi, right? And provided that you are using u, which is just an unitary matrix, u dagger times u is equal to identity, right? So this means that this kinetic term is automatically invariant under local non-abelian gauge transformation. Right? So this is true for scalar field. I mean, the same also apply for the spin 1 field. I mean, the fact that the covariant derivative transform homogeneously ensure that the kinetic term of scalars or spin 1 are automatically gauge invariant. So the only thing that we need to take care of now, is really the kinetic term of the gauge fields themselves. Right? This F mu nu pieces that we added to the Lagrangian to describe the motion of this gauge field. What is the generalization of this piece. So now you will realize that actually F mu nu, no, if you take the generalization, so d mu a nu minus d nu a mu, actually doesn't transform nicely under this transformation law of the gauge field. I mean, because you have plenty of derivatives here, the derivative will act on here, it will act there, it will act there, and since the matrices don't commute with each other, you will have a lot of pieces that are left when you are trying to transform these things. And actually, here you will get nice transformation property if you add actually another piece to this field strength, which is simply the commutator of a mu a nu. So again, for QED, this is automatically 0, right? Because QED, again, is abelian, so the field commute with each other. So this commutator is 0. But for non-abelian gauge transformation, you have a non-vanishing commutator. And then, I mean, using this transformation law of the gauge field, you can easily convince yourself that F mu nu transform as U, F mu nu, U minus 1. So again, is homogeneous transformation, There is no derivative, space-time derivative acting on the transformation matrix U. So this means that now the trace of F mu nu will be automatically gauge invariant also, right? Because this is transforming as trace U, F mu nu, U minus 1. The other one is U, F mu nu, U minus 1, right? So U minus 1 is identity. And since the trace is invariant on the cyclic permutation, this is nothing else than the trace of U, F mu nu, U minus 1, right? Then you move this U minus 1 there. The U minus 1 U is equal to identity again. So this is a trace of F mu nu, right? So again, you have been able to write something which is gauge invariant. And that contains clearly the kinematic propagation of the gauge field. So this means that you can now write the non-abelian equivalent of the QED kinetic term, which is minus 1/4. Again, this 1/4 is just some arbitrary normalization of the field. It doesn't matter. The trace of F mu nu. Right. Is it clear to everybody? Right. That's probably something that you have learned already, but it's always nice to see how everything connects with each other. Okay. So now let's look a little bit at the content of this kinetic term, right? So the non-trivial pieces now is this non-abelian interaction among gauge field, right? The commutator of a mu with a nu. So this means that F mu nu squared will contain a piece which is, okay, d squared a squared, so that's the usual kinetic term, but it will also contain a piece which is g, a derivative acting on a, times a squared, and it will contain another piece which is g squared a to the 4th. Right? So now suddenly, in order for the kinetic term to be invariant under this local gauge transformation, I'm forced to introduce some interaction among the gauge boson. So we'll have an interaction among 3 gauge boson, like this, right? This piece, which will be proportional to the derivative of one field, so it will be proportional to the momentum of one particle, one momentum. And then, so it will be proportional to g times p, right? The momentum of typical momentum that enters into these diagrams. And I also have quartic interaction among 4 gauge boson, which is proportional to g squared. Right? But that's exactly what I want, right? I want an interaction among 3 gauge boson. And that's something that was necessary to be consistent with the conservation of the electric charge here. Right? So clearly now I want to find a gauge symmetry, a non-abelian gauge symmetry, right, to describe this interaction among two W's and one photon. So here it's a little bit of math, right? What is a symmetry? What are the possible symmetry that will contain at least 3 gauge bosons, right? I want the photon, I want the W plus and the W minus. So this is what we call model building. You know, you try to embed all the particles that you know into some possible symmetries. So that was an exercise that several people have done in the early 70s. The simplest model was proposed actually by Grojean and Grojean. I think it was 72. It's just an SU2 model. So SU2, I don't know, well, SU2 should be familiar to you from quantum mechanics, right? So there are 3 generators, the 3 Pauli matrices. So 3 generator means that you have 3 gauge boson. Each generator of the group corresponds to 1 gauge boson. So that's in principle what you want, right? You have the photon, W plus, W minus. So you can really identify those 3 gauge boson with a 3 generator of SU2. The problem with this model is that he has a prediction, right? So something that you know, I mean, the trace of the generator of SU2, the trace of the Pauli matrices are 0. Which means that actually the trace of all possible representation of the group should vanish. So if you want to embed, let's say, the photon as 1 generator of SU2, means that the trace of the electric charge in any representation should be equal to 0. So what are the possible representations that we want to build? I mean, here, certainly, you want an interaction between the neutrino and the electron. So that should be part of one representation of SU2. But the trace of the electric charge here is non-zero, right? The neutrino has an electric charge 0. The electron has an electric charge -1. So the trace, so the sum of the electric charge in all possible components of the irreducible representation is not 0. So this means that you need to add 1 extra particle of electric charge +1. So you want to call it X. So here it's -1. Here it will have an electric charge +1 in order to be consistent with mathematics, in order to form a representation under the SU2 symmetries. Right? So one prediction really of this Grojean-Grojean model is that there should exist 1 extra particle, X plus, which has an electric charge +1. Right? It's just mathematical consistency of the model. So of course, experimentalists now, I mean, have tried to very hard to identify this extra particle that was predicted, right? And this particle was never found, actually. So it means that the Grojean-Grojean model is not a good description of this interaction between the W and the photon. So there are other gauge group that you can consider, you know, where you don't introduce extra gauge boson. So you do all your math with the W plus and W minus and the photon. So here I've used SU2, which is maybe, I mean, most famous group of dimension 3. There is other group which is SU11, or even there is an exceptional Lie group which is E2. For mathematical reason, I mean, those groups are not good candidates either to describe nature. For instance, I think E2 has only 1 unitary representation, which is actually the trivial representation. So it means that you cannot embed the electron and the neutrino into representation of E2. So very quickly, let's say for mathematical reason, you discard those 2 cases, right? So it means that, you know, now you have really exhausted all possibilities, you know, where you don't introduce any extra gauge boson. So you have exhausted all possibility where you have no new forces, right? So this was a list of models with no new forces, right? What I mean by no new forces, I'm trying to describe things with only the gauge boson that I know should exist. The photon, the W plus and W minus. And the prediction of those models with no new forces was that you are forced to introduce new matter. So no new forces means new matter should exist in nature. So that, again, you know, that was a viable model of nature, but that's not the way nature went. I mean, nature actually instead decided to introduce new forces, and actually you can build some model with new forces but no new matter. So that, in a sense, a dichotomy. There was a choice between new forces or no new matter, or no new forces and new matter. And nature has chosen the other things, which is, I mean, what we call the George Glashow, Salam, and Weinberg model, right? So the standard model. And this standard model is based on a group which is SU2 cross U1. So now, indeed, you have 4-gauge boson, right? SU2 is dimension 3, U1 is dimension 1, so you have 4-gauge boson. And the photon, actually, is a mixture of the generator, the diagonal generator of SU2 and the diagonal generator of U1. So here, the way you want to embed electromagnetism into this group is that the electric charge will correspond actually to the generator, the diagonal generator of SU2, so it's T3 plus Y. This is hypercharge associated to this U1 symmetry. So electromagnetism is not a fundamental interaction of the standard model. Electromagnetism is actually a combination of the fundamental forces of nature. Right? There is U1, which is called hypercharge forces. And SU2 is what we call the weak forces. Right? And electromagnetism is only one particular linear combination of those forces. We will discuss how this electromagnetism actually emerged. It emerged through the Higgs mechanism, so through a spontaneous breaking of the symmetry in nature. So the fact that the vacuum actually doesn't respect the full symmetry. So this is the symmetry of the Lagrangian. So this is the symmetry of all your interaction, but the vacuum is breaking this symmetry spontaneously. Okay? Good. So, yeah, question? Yeah, so here what I'm trying to do is simply try to find a way, you know, to describe this photon and W plus and W minus. So somehow I need to associate those gauge boson to generator of a symmetry. So I first started, you know, to associate them to symmetries that are of dimension 3, that only involve 3 generators. So SU2 is one candidate. But for some reason, it doesn't work because, you know, you are predicting a new particle. Then the only solution now is to extend a little bit the symmetry, so to consider groups which are larger than SU2. So you have more gauge boson. And the W, the photon, and the Z that we are going to introduce, because now we have 4 gauge boson, those are actually combination of the 4 generator of SU2 cross U1. Okay? Good. Yes. So of course, now I still need, you know, to find representation of all my particle into representation of SU2 cross U1, right? So I want to know how those different particles of the standard model transform under this symmetry. So again, what I'm really trying to do, you know, is to find this type of interaction, a neutrino with an electron with a W. So this means that the electron and the neutrino should be part of the same doublet. Should be part of the same representation of SU2. So certainly, you want to do something like that, electron neutrino into a doublet of SU2. I mean, you know that a doublet is a good irreducible representation of SU2. I mean, from quantum mechanics, that's maybe the first thing that you learn about group theory, right? That you have a doublet representation of SU2. Fine. So that is telling you that how those two particles actually transform under SU2. So now the thing that you want to do is to identify the hypercharge. So you want to identify the hypercharge, so these quantum numbers of this doublet under this U1 representation. So what does it mean that you embed those particles into irreducible representation? It means that you need to find the same hypercharge for those two particles. It is hypercharge of a doublet, so the two particles should have the same hypercharge. And clearly here you see that from there is one solution, right? I mean T3, so it's plus 1/2 for the upper component of the doublet, it's minus 1/2 for the lower component of the doublet. The electric charge of those particles is 0 here, is minus 1 here. And clearly you see that if the hypercharge is equal to minus 1/2, so Q hypercharge is minus 1/2, minus 1/2, you indeed satisfy this relation. The electric charge of the neutrino is minus 1/2 plus 1/2 for T3 is equal to 0. And for the electron is minus 1/2 minus 1/2 is minus 1. Right? So here we found how to embed the electron and the neutrino into representation of SU2 cross U1. So that's something that we denote by a 2, because it's a doublet of SU2, and hypercharge minus 1/2 as a subscript. Right? So that's really what we say when we write that electron and neutrino are in this representation of SU2 cross U1. So now you could also figure it out that actually you need to group together at least some chirality of the quark. Right? So you have the up quark and the down quark that have electric charge 2/3, minus 1/3 for the down quark, in such a way that the proton, the proton is made of 2 up quark and 1 down quark. So the proton is electric charge twice 2/3 minus 1/3 is equal to plus 1. And the neutron is 1 up quark and 2 down quark. So it's 2/3 minus twice minus 1/3 is equal to 0. And here you can figure it out. I think that it should be 1/6, right? So you can really assign the same hypercharge to the two components of the doublet in such a way that, yes, the electric charge exactly obeys this relation. Right? So the up quark and the down quark are in a doublet with an hypercharge which is 1/6. Is it clear to everybody? Okay. This? So the T3 is just the eigenvalue of the diagonal generator of SU2, right? So the Pauli matrices is 1 minus 1. So here you put a minus, 1/2 just for normalization purpose. Okay. So there is actually one subtlety here, is that the standard model, as we are going to discover in a moment when I'll discuss the pion decay, the standard model is what we call a chiral theory. So the left-handed chirality and the right-handed chiralities of the fermion don't transform in the same way under the gauge symmetries. Right? So it distinguishes the left and the right. So here, you only put actually the left-handed chiralities of the quark into the doublet of SU2, while the right-handed chiralities will be singlet under SU2. So the right-handed chiralities, so up right or down right, they are singlet under SU2. So they are singlet. They don't transform under SU2. They don't interact with the W. It's only the left-handed chiralities that interact with the W. And now, the electric charge is 2/3 minus 1/3. So T3 is equal to 0 because they are not charged under SU2. So it means that the hypercharge, actually, for the right-handed chiralities of the quark is equal to the electric charge. It's 2/3 minus 1/3. So here it's a singlet with hypercharge 2/3 and a singlet with hypercharge minus 1/3. Right? So what we have achieved here is really to identify how the different particle of matter actually transform under this symmetry SU2 cross U1. So probably tomorrow or Thursday I will introduce QCD, so there is still an extra symmetry that is acting on some of those particles which are responsible for the strong interactions. Right? But let's postpone that later. Okay. Yep. So here you have one generator, which is diagonal. I mean, SU2 is what we call rank 1. So you can always make one generator diagonal. And in the doublet representation, the eigenvalue of this diagonal generator is 1 minus 1 or 1/2 minus 1/2. Right? So that's why here T3 is equal to plus 1/2 here for the neutrino, minus 1/2 for the electron. So that's really what we mean by putting things in doublets. So there is a meaning of being upper component or lower component. It's just the eigenvalue of this generator T3. Okay? Any other question? Math question, physics question, whatever. Math and physics are unified, right?
So I suppose we're going to talk about the Higgs later, but I would like to make a question. When you are talking about fermions, you have to consider the singlet representation, which are the right-handed, and the doublet, which are the left-handed. But when you consider Higgs, you just take the doublet representation, and why don't you consider a singlet scalar in standard model? Because it's logical. You can have both singlets and doublets.
You could have X, which is singlet under SU2, but this X wouldn't break the SU2 symmetry. So it wouldn't be responsible for what we call electroic symmetry breaking. It could be indeed part of the X sector, but it has nothing to do with the dynamics of getting a mass to the W and the Z. It's something external. Right? That might have important consequences, I don't know, for the dynamics of the electric phase transition, for whether it's first order, second order phase transition, might depend whether there is indeed a singlet in addition to the doublet. But it's an open question, yes. We haven't observed, what we have observed at the moment is a X doublet, part of the X doublet. We haven't found this X singlet, but it might exist. It might be heavier, whatever, or lighter and weakly coupled, whatever, but we haven't identified such a particle yet.
Could in principle participate in Yukawa interaction?
Yes and no. In the sense that with this X doublet, we are going to discuss exactly what are the interaction of the X with the fermions. And for that, you don't need a singlet. Nonetheless, since it's a singlet, you could also add extra power of the singlet because it doesn't transform in the gauge symmetry. So you add extra power. Just that those extra power will be non-renormalizable interaction again. So they are not fundamental interaction in the Lagrangian. They might come from heavy particles that are integrated out again. But so the answer is that we don't know again. Any other questions? Yeah.
So could you repeat the part that you said that Glashow predicted an extra particle because of the trace?
Yes. So you have SU2 symmetry. So SU2 means that here, you want to identify some unitary matrix of determinant equal to 1. Right? That's what this US means, contrary to U2. So determinant is 1, means that the trace of the generator are equal to 0. So what does it mean, that the trace of the generator? So now you want to see electromagnetism, you want to see the photon as one generator of SU2. So it means that in every irreducible representation, the sum of the electric charge should be equal to 0. So if you want to have, if you want to build an irreducible representation that involves the electron and the neutrino, the only option is to add an extra particle which has an electric charge +1. That's the only way to get a trace which is 0 inside this irreducible representation. Okay? Good. So what, yes. So yeah, so there were these two candidates, I mean, theorists try to identify models that are mathematically consistent, and they were left with those basically two prime hypotheses. Either you have new matter, or either you have new forces. And now it's an experimental question, which model nature have actually chosen, right? And for that, there were an important experiment, which is called Gargamel, that actually identified this extra gauge boson, so the fourth gauge boson here. Right? So I told you that here you have four, it's dimension 4, so you have a fourth gauge boson. And Gargamel is the first experiment that really have found some experimental evidence of this extra gauge boson, which is called an extra neutral current. So neutral current simply is something equivalent to the photon. So the photon, mediate interaction which are electrically neutral. So it turns out that here the fourth gauge boson will also be electrically neutral. And the first experiment to really find evidence of this is Gargamel. So the difficulty was indeed to identify here a new force, which in a sense is very similar to electromagnetism because it will be also electrically neutral, right? So you need to find an experiment where you are able to distinguish something from electromagnetism. So the idea was to look at the processes, that cannot be mediated by electromagnetism. And one good candidate is certainly some processes with neutrino, because the neutrino, again, are electrically neutral, so they cannot interact with the photon. So the idea of Gargamel was really to try to look at an experiment, a new interaction that is acting on neutrino, and that cannot also be mediated with a W. So the process that they looked at is muon neutrino with an electron. They looked at the scattering of those two particles, nu mu e. Right. So what are the possible diagrams that correspond to this interaction? So you could think, well, why not, for instance, an interaction with a W, right? I have nu mu, I have the electron. So here it's an electric charge -1, 0. So here, something that respects electric charge, certainly. Nu mu, 0, electron. Right? That seems possible, except that the W interaction actually is diagonal in flavor space. So you have an interaction of a W with an electron and then a muon with an electron neutrino, but not with a muon neutrino. This violates what we call the flavor symmetry. So this interaction doesn't exist. Similarly, this doesn't exist, right? Clearly here you cannot have an interaction, let's say, nu mu, with a photon, right? So this vertex exists, but this one doesn't exist, right? Because again, the neutrino doesn't interact with the photon. So the only thing that was left with, if you see such an interaction, it could only be mediated with a new electrically neutral current, nu mu, the Z gauge boson, that interact with the electron like this. So that's the only way, classically, that you could observe such a scattering of a muon neutrino over an electron. Of course, quantum mechanically things are a little bit more complicated. There is another diagram that you can write with photon and W that could mediate these interactions. So here, nice loop diagrams like this. No, is this? right? So here you have, what is it? Nu mu, W, you have the muon here, nu mu, you have the W, and then you have the electron, the neutrino electron, and the electron, right? So here, I don't know if you have the muon here, this is W plus, W electron, so minus, and here it's electric charge, right? Is conserved at any piece of this diagram. So quantum mechanically, indeed, you could have this process which is generated only with a W, and you don't need to introduce the Z boson. But clearly here, since it's a quantum mechanical process, it's expected to be subdominant compared to this one, right? So if there exists a Z, then you expect to see a large rate for this scattering process. If the rate is small, then maybe the Z doesn't exist, and it's only mediated by the exchange of a W. So people just produce a beam of electron, a beam of muon neutrino, which, by the way, is easy. We're going to discuss probably tomorrow now why it's easy to get a beam of muon, neutrino muon. And then they just count, right? They just count the number of events of this type as they find a large rate, and that was a clear indication that indeed a Z boson exists in nature. So that was, I think, it was 50 years ago, right? So 1974. So that's the Gargamel experiment. Gargamel, 74. It was again an experiment at CERN. I think it's a first big discovery of CERN that made a nice things and discovered something new. They discovered the evidence that the Z boson exists. Of course, this is still an indirect evidence, right? They just look at, they just counting the number of events like that. It's a large rate, so probably the Z exists. And it took 10 more years, basically, to be able to produce the Z boson by collision of electron and positron. So that's UA1 and UA2. That was the first experiment really to be able to produce a Z and a W gauge boson. So 83. Right? So that's indirect evidence. But everybody was convinced, right? There were no doubt that the Z boson exists. And then UA1 and UA2, UA1 and 2 in 83 discover the W plus, W minus, and Z boson. At CERN again, right? Yes, indeed. Yes. Okay, any question at this stage? I mean, we are building the standard model by experimental discovery, right? Okay, so 5 more minutes. Maybe I can quickly explain to you, actually, to make the connection between the Fermi theory and this gauge description. What I've done here is to introduce a W on the Z boson, and somehow I told you that these are the particles that are at the origin of these 4 Fermi interactions. So let's try to understand that a little bit better. This is what we call, effective field theory. So you start with a theory at high energy that describes the dynamics of the W and the Z, and then we look at an effective theory at energy below the mass of the W and the Z. So these particles are not propagating degrees of freedom any longer. They are just classical field. What it means that you can replace actually those fields by their expectation value, by their equation of motion. So you start with a Lagrangian, that really describe this gauge theory. So exactly like what we have written with all this covariant kinetic term, this kinetic term for the gauge field. And then you integrate out, so you just look at the dynamics of all this field at energy below the mass of AV particle. So here I'm cheating a little bit because I don't explain how I generate the mass of the W and the Z. It's just a fact that the W and the Z have a mass. So I write all my Lagrangian for the gauge symmetry, and I add by hand a mass for the W. So you know exactly how to write this Lagrangian. It's just the interaction which is coming from the kinetic term of, let's say, the electron, the neutrino on the quark, right? So you have this kinetic term, which is okay. This Dirac-Lagrangian, right? Psi bar gamma 0 d mu psi, or minus the mass of the electron, whatever, psi, that's the Dirac-Lagrangian. And here, this covariant derivative contains now the interaction of all the fermion with the gauge boson, right? So it contains the interaction with W plus, W minus, the Z, and actually this fourth gauge boson that we call the B gauge boson. And we will see how they connect with the photon, right? So at the end of the day, when you keep all the interaction between fermion and gauge boson, you have something like that, right? W mu plus, a current, J mu, eta mu nu, okay, plus J mu, so current minus J plus mu, and then I add by hand a mass term for the gauge field. So minus the mass of the W squared, W mu plus W mu minus, right? Okay. So this is just a mass term for the gauge field. Okay. And here, this current is just the current that basically we introduced before. It was written somewhere here. That is this the weak current, right? So now let's look at this Lagrangian, at the dynamics of this Lagrangian at energy below the mass of the W. So what I want to do is just replace the W by its equation of motion. So I want to make sure that the variation of the Lagrangian with respect to the W field is equal to 0. That's how the equation of motion are defined, right? So 0 is equal to J, or J minus mu. So this is a derivative with this W plus, and there is another one here, minus the mass of the W squared times W mu minus, right? So this is equal to 0. It means that classically, the W field, so W mu minus, is equal to G divided by mW squared times the current, times the fermionic current, right? That's the classical equation of motion, right? That's what happens when you don't have enough energy to excite these degrees of freedom. And now get an effective Lagrangian by replacing the W by its equation of motion in the Lagrangian, right? So that's quite simple. Means that the Lagrangian is equal to G, the gauge coupling, W plus, so it's just the complex conjugate of this, so it's G divided by M W squared, J plus mu, right? So that was this W mu plus that I replaced by this equation of motion, times J mu minus, plus G, W mu minus is G divided by mW squared, G mu minus times J plus mu, plus now a minus the mass of the W squared times the square of this, so G divided by mW squared, G plus mu, G divided by mW squared, G mu minus, right? And now, if I haven't done any mistake, this is nothing else than G squared divided by mW squared, G mu plus G mu minus, right? So that's exactly the Fermi Lagrangian that we have introduced earlier to describe these decays of the muon and the neutrino. And now we have been able to identify what the Fermi constant is, right? The Fermi constant is nothing else than G squared divided by the mass of the W squared. Right? So we have a fundamental understanding of where this effective theory is coming from. This effective theory is nothing else than the description of the propagation of a W at energy below the mass of the W. Right. So the only thing that is left to understand is actually where the mass of the W is coming from, right? Because here, I put by hand in my Lagrangian this mass for the W. But if you remember how the gauge field transform, right? I mean, this complicated transformation law, you will realize that this mass term is not gauge invariant. So here, I've cheated a little bit, right? I've written a Lagrangian which is not really invariant under all the symmetries. So I need to tell you how I do generate the mass of the W. And that's the X mechanism that we will discuss tomorrow. So the X mechanism is responsible for the mass of the W. We will understand also that it is also responsible for the mass of the electron, the mass of the quarks, right? But that's something that you can dream of tonight, and we will explain to you tomorrow. Thanks.
Questions?
Thank you for the lecture. It was really nice. My question is about the explicit symmetry breaking term that you introduced.
Yes.
It will introduce kind of divergences in your theory, right?
Divergences in the theory. Well, if you do it properly, there is no divergences. I mean, X mechanism is precisely a way to avoid any divergence.
I mean, with explicit symmetry breaking.
Yes, right.
Every explicit symmetry breaking that introduced in the standard model introduce a divergence in the model or not?
In the standard model, I mean, all the divergences that occurs when you do quantum correction actually can be reabsorbed by renormalization. So that's why we call that. I mean, we say that the standard model is renormalizable, so there is no divergences. The only somehow, I mean, divergences, but it's not really a divergences in terms of quantum field theory, is associated to the hierarchy problem. So we would like to see what are the quantum correction to the mass of the Higgs boson. So this is what is called these famous quadratic divergences of the Higgs mass. So again, it's not really a divergences in the sense of quantum field theory, but it means that the Higgs mass will be sensitive to very high energy physics. But that's something we will discuss, and it will also be discussed next week by Marcus Luthi. So you will understand really what the hierarchy problem means. But yeah, in the standard model, there is no divergences.
Okay, another question. You consider the fundamental representation of SU2.
Mm-hmm.
Why all the fields in the standard model are in the fundamental representation? I know it is a tough question because I ask everyone that I can this question because it's something that bothers me.
Yeah, I mean, if you want to use non-unitary representation, it means that you don't have a conservation of probability and things like that. So I think it's not a good description of nature in terms of particle and interaction. Sometimes in string theory, you can use some non-unitary representation for describing things, but yeah, in quantum field theory, you want unitary representation to be able to realize your symmetry linearly among the particles.
Okay, but you could have considered kind of spinorial representation and stuff like that?
You could, yes. I mean,
but why not? Just experiment.
Well, you start with a simpler thing. If it works, you stop, right? And, there are models, for instance, of ground unified theory with SO10, where indeed you embed all the particles of the standard model into spinorial representation of SO10. Mm-hmm. But this is still a unitary representation, right? It's just a spinorial, so it's a little bit more complicated, but it's still unitary representation.
Okay, thank you.
You need to imagine that people were trying to use for the first time Lie theory for particle physics. You needed to start with the simplest thing. You cannot imagine, something which is more complicated. Otherwise, you're never able to find it, right? Sure. 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 But in a sense, we were lucky that it worked with fundamental representation.
Thank you for the talk. I wanted to ask about, you mentioned we could predict the vertex between the two W's and the photon. How can you know just by looking at that vertex that it's a nanobabelian interaction? Because I'm a little bit familiar with group theory, but I cannot imagine just by looking at physics what it means.
Again, it's because abelian theory doesn't have interaction among the gauge boson. As we have constructed, right, the kinetic term for the gauge field for the photon doesn't predict any interaction of the photon with itself. It's really a term that appears in non-abelian interaction due to this commutator that you need to introduce in the field strength.
Oh, thank you.
That, I mean, yeah, interaction among gauge boson is really an indication that you have non-abelian symmetries.
Okay, thank you very much.
Thank you for the lecture as well. I was wondering when you talked about how Glashow, Georgi made the second model, the SU2 cross U1 model, and then you mentioned that the Z and the photon bosons are mixtures of both the generators, but that was fully described by the Higgs mechanism. Yes. But by the time they built this model, did they already know they had to be mixed, even without the Higgs mechanism?
I mean, they knew it from this relation between the hypercharge and the electric charge, right? So this is an indication that the gauge boson need to mix among each other. But really, to understand that concretely, you need to rely on the Higgs mechanism. Right? It will become clear when we discuss the Higgs. I mean, you say, of course, it's obvious, right? It's obvious now, but took some time. Yes.
Yeah. So they knew it had to be mixed, but they didn't know, for example, on the ratio between the mass of the Z and the double boson, which come from the symmetry breaking or other. Okay, you know, it had to happen, and Peter Higgs came in.
Yeah.
I see. Okay.
It's Weinberg in the sense that understood
Professor,
that. But,
excuse me. Could you explain again the Lagrangian in terms of diagrams? I mean, you reduce to four interaction, just 1 point.
So you mean this Lagrangian here? So
the final.
Oh, this one.
This is.
So this is just
four particles.
The
in
four.
one
I mean, here J. You know, I mean, okay, we can write again J, right? J plus mu is something like, I don't know, probably the neutron, gamma mu, the proton, plus, I don't know, electron bar, gamma mu, the neutrino, plus, I mean, at the end of the day, we are going to learn tomorrow that that's not the exact form. It's a little bit more complicated, but for the moment, you can stick to this, right? So mu bar, gamma mu, nu mu, right? And actually now, I mean, we have grown-up people, so we know that the proton and neutron are not elementary particles, so you need actually to replace that with a up and down quark, right? So here it will be probably down quark, bar, gamma mu, up, right? So that's what J is, right?
In terms of diagrams, is just 1 point.
So here, yes. So here it's an effective Lagrangian. So it's really this interaction, right? You just take the squared of this. So the squared of this means an interaction among 4 fermions.
Okay. Thank you.
No more questions?
Can you comment how this experiment was done? I mean, how they produced the mu, and how did they know that it was the neutrino mu? How did they know that it's a neutrino? Because neutrino is tough to detect, right?
Yes, yes. So for that, you need to look at the decay of the pion. It turns out that the decay of the pion will produce essentially muon and not electron. Okay. So, but that's something I need to discuss tomorrow. The pion decay is a fantastic thing that will actually reveal the right structure of this weak interaction. So here, for the moment, I told you that it's just a vector interaction, right? I introduced gamma mu.
Yes.
But what we are going to discover tomorrow by trying to explain the pion decay is that actually has a structure which is vector minus axial. This is V minus A.
Mm-hmm.
So that's really explain why the pion decays essentially into muon and not into electron.
Okay.
So here, this muon, this neutrino muon are coming from the decay of the pion.
Mm-hmm. But in the chamber, you can't see the neutrino, right? So you just see after the decay electrons
Yes,
appearing.
Right. Yeah, you reconstruct. So here you reconstruct the final state just by looking at missing momentum and energy.
Oh, nice.
So you don't really see it, but you see that there is a particle that carries energy and momentum, and it has to be a muon neutrino. Yeah.
Nice. Thanks.
Okay. Then let's thank Christophe again. And we reconvene in half an hour.